session number 6, multi-view and robot vision. So thank you for the attendees and the speakers. We are a little bit late on the schedule, so I will please all the speakers to stay in time with their talk. So the first speaker is Marco Orthinger, who will talk about efficient view clustering and selection for city-scale 3D reconstruction. Thank you.
Hello everyone, can you hear me? Yes? Hello everyone, my name is Marco and I'm here to present my work on efficient view clustering and selection for city-scale 3D reconstruction. This is a joint work with my supervisors at VisLab Ambarella, Paolo Zani and Paolo Medici, and with my supervisor at University of Parma, Massimo Bertozzi. So the problem we are considering here is that we have a fleet of autonomous vehicles going around the cities, and we would like to perform 3D reconstruction on these very large and redundant data sets after the acquisition pipeline. So we start from two key insights. The first is that each image shares common visibility information only with a local neighborhood of other images, because the vehicle visit very different places during the acquisition part. And the second is that these data sets are very redundant for two reasons. First of all, because we have a lot of cameras which acquire data at a high frame rate. And secondly, vehicles might revisit the same place multiple times. So we would like to cluster and select these images. Our proposal is to place two intermediate steps between structure for motion and multi-view stereo, and namely to have a view clustering algorithm that cluster views based on shared visibility information, and then to select within each cluster an optimal subset of views for each cluster to reconstruct. I would like to stress here that the naive solution that one may think of clustering images based on temporal information from videos, this does not work for two reasons. First of all, because with multi-camera rigs, the optimal viewpoints might be acquired in two very different time instants. And also, if you revisit the same place multiple times, you would create different clusters each time. So it just doesn't work. So let's start from the view clustering algorithm. The input is a set of what we call calibrated images. Well, what I mean here is that a structure from motion algorithm has been applied to extract internal parameters, poses for each image, and a set of sparse key points. And what we would like to get is a set of independent and partially overlapping clusters of cameras and key points. And these cameras should have a common visibility to reconstruct the cluster. Conceptually, the algorithm is very simple. What we do is we just build a 2D grid on the XY plane with a given block size and a certain degree of overlap. We do this, of course, in the spatial range defined by the key points in the world frame. Then we assign each key point to the corresponding block by projecting the coordinates, and each camera to all the blocks that has associated key points. We do this simply by having the tracks from the structure for motion, and also we limit the maximum distance between the camera origin and the cluster center. And finally, we iteratively merge clusters having few cameras with their neighbors, because you still need a minimum amount of views for 3D reconstruction. Otherwise, you just don't have enough visual information for inferring the model. The advantage of this approach with respect to some state-of-the-art models that you can find is that other works are specifically designed for very different scenarios, such as architectural datasets. So it's very famous, some works called Building Rome in a Day or something like that, where you reconstruct the Colosseum and other architectural buildings. The problem with those methods is that they compute the so-called similarity matrix in advance. So this is a matrix where you have a pairwise score for each possible pair of cameras. And this scales quadratically, of course, in the number of images, and it is just impractical in our scenario. While using the proposed algorithm that I explained before, you're guaranteed that, first of all, a camera can be associated to very few clusters, so typically one cluster and its immediate neighbors. This is by design. And also each block can be processed in parallel, so this is what allows the algorithm to scale up arbitrarily. Here you can find a visualization of the inner workings of the algorithm. So on the left, you see the row 2D grid built from structure for motion output, where you just have the key points and the row grid. In the center, there is the full sequence that is clustered and filtered, where you see, for example, all the blocks with no key points or with key points very distant from the trajectory that are simply removed. And each cluster is represented with its borders and in a different color. And on the right, you see the same figure, but in greater detail, where you can also appreciate the overlapping step. Remember that we also have cameras in each cluster. I show here only the key points because it's easier to visualize, but then we will visualize cameras as well. And speaking of cameras, once you have all these clusters that are separated independently, these clusters might still be very redundant. So what we do is that we apply a view selection algorithm to each cluster separately in order to select somehow the optimal subset of cameras to enable 3D reconstruction in an efficient way. Our proposal is to formulate a very simple integer linear programming problem with binary variables xi representing the cameras in the cluster. And the objective goal, of course, is to minimize the number of cameras. And in order to guarantee that these cameras still contain sufficient information for 3D reconstruction, we impose 3 constraints. So the first one is that in any case, you need to select a minimum number of cameras. And we find it really beneficial to initialize the solver with this number of cameras having the best visibility, where visibility is just defined by the number of key points that you actually see. Then we impose the constraint that each point should be seen by at least a minimum number of cameras again, because you want to avoid that a point is seen only by one camera, because otherwise you do not have nothing to triangulate with. And finally, we would like to have each key point to be, let's say, successfully matched with at least a minimum number of cameras. This can be defined in a lot of ways. You can just impose that each key point is seen by a lot of cameras and then hope that these cameras are well distributed. Or you can compute, this is what we do, we compute a triangulation angle between all the cameras, and then we impose that these triangulation angles are within a certain range. So this allows you to have well-distributed cameras by design. Here you can see what happens when you go from clustering to selection. Here the clusters are represented with blue key points and red cameras. I hope you can also see the little black arrows that are the optical axis of the cameras. So I reported here 3 very common situations in urban scenarios. On the left, you see a cluster where all the cameras are outside the cluster borders. And what the algorithm does, it just reduces the number of cameras while keeping approximately the same distribution. In the center, a very complicated case, but it's really unavoidable. So it's when the vehicle trajectory intersects the cluster, and the algorithm correctly selects 2 disjoint sets of cameras that will reconstruct the cluster. And finally, on the right, there is let's say, a generalization to very complex trajectories, such as roundabouts that are very common in our scenarios. From a qualitative point of view, what we want is to have a set of images that actually represent the same place in the world. And you can see here that the set, this is only a subset, of course, of the images associated to a cluster, but you can see that the shared visual content is there. And this is what we wanted to obtain. And on the right, for these 2 corresponding sets of images, you see the 3D model. These images come from a custom dataset, so we acquired that in Parma with our vehicles. And the 3D model is computed with a state-of-the-art multi-view stereo algorithm. The important part here is that at this point you can use any reconstruction algorithm that you want. So if you want to use deep learning, if you want to use Colmap, if you want to use your own stack, it's not a problem. The goal of the work is to produce the input for this algorithm, because otherwise you would have to consider all the data set, and it's just not possible. So another experiment that we conducted is to verify that the reconstruction obtained by merging individual clusters and the reconstruction obtained, let's say, in a full batch are comparable, at least visually. So we don't have numerical ground truth in 3D to provide some quantitative results, but we can see that the quality is indeed comparable. The main difference is concentrated in the rotary center, where you have a very complex place. So you have almost identical trees, and in the full batch case on the left, multi-view stereo benefits from additional redundancy, while if you just reduce the views and merge clusters, you get these little holes. But we are working on a post-processing step to merge the clusters properly. Right now, it's just done by placing them in a correct place, so nothing really smart. And finally, from a numerical point of view, the problem with comparing with state-of-the-art is that they target a very different scenario where this scalability was not really an issue. We can see that our approach can process approximately 4,000 images per minute on a consumer CPU. So I have tested it on my middle-end computer. Differently, also from the previous method, our key result is that we scale linearly with the dataset size. And this plot is done without massive parallelization. So it's done just by summing the running times of all the clusters. And if you have a big cluster with a lot of CPUs, you can process each cluster in parallel. It just depends on what you have. So I leave you with some references. Thank you for listening, and I'm here for questions. And also, if you have questions afterwards, we can meet outside. Thanks.
So thank you. Thank you so much for the presentation. Any questions from the audience? Questions?
Thank you, Marco, for a very great presentation. I just want to ask, in the beginning, you first apply this sparse reconstruction.
Yeah.
And in order to get the camera pose and also all the parameters and all that. So is it not a computationally expensive? First you apply a sparse reconstruction and then again you get multi-view stereo, or at the end you again get the reconstruction. So what is the motivation? I a little bit lost.
Okay, so what you do typically in 3D reconstruction, you do a first phase where you compute poses of images, and this is structure from motion. And then when you have poses, you can reconstruct the depth for each pixel, and this is multi-view stereo. So in our software stack at VisLab, we already had a very large-scale bundle adjustment procedure to compute poses, and we just started from there. And also you have to consider that all these procedures are offline, so processing time is not really an issue unless you really spend ages in computing, but if it takes some hours, it's not really an issue for us. What we want is a large-scale and precise model. That's what we aim for.
Second question.
Thank you for the presentation. I have actually two questions. The first one is, so you're interested in large-scale model and the reconstruction, 3D reconstruction that you make. How is the resolution of it?
Well, we have full HD images, so you have 1 point for each pixel approximately. Of course, not in the sky or something like that, but the resolution of images is 1920 times 1080, so that's the resolution we use. But again, you can use whatever resolution you want. It's not really an issue.
And the second question is about the reduction of the cameras, either make locally for every cluster that you make, or is globally in the whole scene?
Okay, so this is really controllable. We require at least 20 cameras for clusters, otherwise we observe that you don't just have enough visual information for reconstructing the clusters, but it's a parameter that you can specify in the optimization problem. You set the minimum number of cameras that you want. So if you want a bigger reduction, you can lower it, or if you want more information and you want to be more redundant, you can higher it.
But this is locally or is globally?
It's locally for each cluster. Because then we process clusters in parallel, so that's what we want.
Thank you.
So very last question, quick question, please.
You can ask question afterwards also. So.
No, yeah.
Thank you for presentation. This was very interesting. So I was curious about the key points. Like, is there any upper bound about the key points? How many key points are you are using?
You mean for clustering?
Yes.
Okay, so in the first phase, it really depends on the image itself, of course, because if you see a building, you will have a lot of key points, otherwise not. But it's some thousand key points for image, per each image.
Okay, thank you.
It's the standard from structure for motion. So you get very sparse but very good key points usually.
So let's thank the speaker.
Thank you.
Thank you so much. So now we have the second speaker is Livi Raivio, who will talk about online panoptic 3D reconstruction as a linear assignment problem.
Google Slides. I had the Google Slides. Do I need to log in somewhere? How does that work? I can log into browser or something. Yeah, but where they shared with you the slides. Oh, I can. Excuse me, how do you get the ad mark? Because, yeah. Thank you. Sorry about this.
Any problem with the presentation?
Yeah, I can. Sorry about this. I have the Google Slides and I have to log into the Google Drive to get those, but I'll start soon.
Full screen. Okay.
Thanks. Sorry about that. So, hello, my name is Leevi, and I'll talk to you about panoptic 3D reconstruction. So I'm from Tampere University, and this work was conducted at Tampere University last year. So, what actually is panoptic segmentation? It's basically the combination of semantic segmentation and instance segmentation. So we want to segment and classify both stuff and things. So stuff is basically all the amorphous areas in the image, like road or buildings or the sky, and things are all the quantifiable objects. And we want to give each pixel in the image both a class and a instance ID. So for example, in the image on the right, you can see the road is colored with the same color at every pixel, so it only has one ID, but all the cars, for example, are identified as individual objects. But for this to be actually usable in, for example, robotics, we need the information in 3D and preferably also in real time, so we have to process data online. And so we need, in addition to the images, also some depth information or then segmented point clouds. And we need to process the point clouds sequentially, so we cannot use the future information, only the past and the present. And the key challenges in this sort of approaches are first and foremost the data association, so on how to actually associate the detected segments in the image to the reconstruction, and then also on how to integrate said information. And this is the overview of our method that we are using. From left to right, first we get the RGB images and segment them with a panoptic segmentation model, and then combine them with depth and camera pose to get a point cloud in the global coordinate frame. Now, in this case, we are using the RGBD images, but we could also be using segmented point clouds if we had those, for example, from a LiDAR or some other similar sensor. And then the point clouds are turned into a voxel grid so that they are easier to process, and those voxel grids match the actual 3D reconstruction, so we get clusters of voxels for each segment in the image. And those are then matched with all the segments in the existing reconstruction, and if we have a match with the segment, then we integrate the new segment into the old one, and if we don't, then we generate a new target segment. And this is then repeated as many times as there are frames in the image, or sorry, at the sequence. And well, I might not have too much time to go into the details, but we'll try. So associating the stuff classes is actually quite easy because we only have one instance ID, so all the detections will be assigned to the same ID. For example, floor segments in the animation are all colored green. However, if we want to associate the thin classes as well, it gets a bit more complicated because they are not necessarily consistent across frames. Like, for example, in image segmentation models, you only get the IDs consistent within the single frame, or in video segmentation only across a small window of frames. And yeah, let's go onward. So this is how we actually solve the association problem. We can assume that the panoptic segmentation model doesn't have any overlaps between segments, and that each segment is originating only from one target, and on the other hand, each target only should be associated with one detection. And so we get a sort of matrix you can see on the right, where each detection segment is basically a row of the matrix, and each target is represented by a column of the matrix, and the cell values are the likelihoods of them matching. And so we want to find the configuration of matches that has the highest combined likelihood. And this can be optimally solved with the Hungarian algorithm, which is quite popular also in multi-object tracking, and this actually doesn't take too much time because we only have to consider the targets that are in the current field of view. And after we have the associations, we can then integrate the data into the reconstruction, and we use the truncated signed distance field method, which has been modified to also include the instance IDs and the class IDs. This is quite similar to the panoptic fusion method that has been published in 2019, and we borrow the algorithm in this work as well. So we basically store the distances to nearest surfaces and the instance IDs and class IDs and update them for each point in the point cloud. And then afterwards we can also generate the triangular mesh if we want to with the marching cubes method. And I highly recommend to check this Voxblocks library if you're interested. It's quite useful for reconstructing these voxel grids. Sorry about that. And yeah, you can read all the tables and the detailed results in the paper, but I'll rather show you a video here. So this is does it start? Okay, I guess I won't show you the video, but it would have been pretty cool. Yeah. So we actually are able to beat our baseline. We get better results than the panoptic fusion when purely processing the data online, and can actually process them in real-time speeds. But we haven't really optimized the code too much, so we could get faster times as well. And let me get to the last slide. Okay, yeah. And if you want to check the videos, for example, the one that I was going to show you, that we cannot see now, you can scan the QR code. There's also the source code and the paper, and all the details. You can actually rerun our experiments if you want to. Otherwise, thanks for listening.
So thank you. It's unfortunate that we couldn't see the video. Any questions from the audience? Yeah, one question.
So, hi, and thanks for your presentation. And I'm interested about what kind of LiDARs or stereo cameras or something you use to get the three-dimensional data.
We use the Microsoft Azure Kinect RGBD camera, but this is basically agnostic to any sensor, so you could use any RGBD or stereo camera or a LiDAR. Or you just have to have basically the segmented point clouds somehow.
Okay, we have another question.
Thank you for the presentation. I have a question about the segmentation part. Actually, you do it frame by frame, or you use the temporal information to accelerate the process of segmentation?
Currently, frame by frame, because we have to process it quite fast. But we have also considered the video segmentation stuff as well, but it's ongoing.
Okay, thank you.
So, other questions? So, no questions, and let's thank the speaker again.
Thank you.
We have now the third presentation. I have two names listed here, so it's Mohamed Zoahib and Alessio Del Bue. I suppose Mohamed will give the talk, and the talk will be 3D key points estimation from single view RGB images.
One moment.
Hello, everyone. I'm excited to present my work to you, 3D key points estimation from single view RGB images. My name is Mohammad Zohaib, and I'm a PhD student at Pavia's Italian Institute of Technology. Before going into the details, I'd like to discuss first why we are focusing more on key points. What are the key points, and how could we use them for downstream tasks? So here's an example. I'd like to start with this. You can see an object on the slide. Like, can you understand, can you recognize what object is this? Is this an aeroplane? No, this is a chair. Okay, so how could we recognize this object? This is a chair, this is not an aeroplane. Based on appearance, based on geometry, or the structure, which is represented using 2000 points. Okay, let me reduce the number of points. Can we still recognize this is a chair? Okay, nice. What about this? Little bit, okay, sure. But still we can recognize the shape or the structure of the object. Okay, let me move a little bit more. What about 200 points? We are using only 200 points. Still, little bit we can identify. What about this? Now we have only 12 points. Can we recognize this is a chair? No, this is very, very difficult to understand. Okay, what about these? These are the same 12 points. But still, like, we can use this information, these 12 points for identification. Like these 12 points are the points from the same point cloud. We can a little bit identify, or even we can rotate this for visual understanding. So if we compare the last two, both are 12. This one is the one highlighted in a box are 12, and the second one is also 12. But the one does not, one set of key point does not explicitly explain the geometry or the shape or structure of an object either, whereas the last one can highlight the structure of the object in a better way. So we can say the key points are those points that can be used, those minimum points that can be used to represent a structure of an object, as highlighted here in the rightmost image. So we can say key points can be used to represent object using a minimum set of points. They require minimum computational resources, minimum time for processing. They are easy to handle for several downstream tasks. For example, finding the correspondences between two objects. For example, if we want to find the correspondences between two objects, we don't need to process all the, we don't need to find the correspondence between all the points in a point cloud. We can just consider our key points. We can use these key points for finding the pose, for finding the relative pose between 2 point clouds, as well as we can also use them for finding the shape, for shape alignment. And there are other several examples we can use where we can use these key points. So here I would like to highlight what is our contribution. So the existing approaches estimates the same key points using point clouds, or there are some approaches that are using multi-view images, multiple views of an object, and they find the 2D key points, and then they use the 2D key points and apply the triangulation for finding the depth. Or there are several other approaches that are using multiple modalities, like they are using images, they are using depth images, and they fuse the features, and then they identify the 3D key points. However, in comparison, what we are doing, we are considering only a single image for estimating 3D key points. Our approach takes a single image as an input, extract 2D features. We convert these features into pixel-wise representation. Please note that the dimension of the pixel-wise representation, it's exactly the same as the dimension of the input image. However, every pixel, instead of representing a pixel value, it's representing a feature. We pass this feature to multi-layer perceptrons, and finally, we estimate 3D key points. We use different loss functions for training of our network. For example, we use position loss for computing the position between the estimated and the ground truth key points. We have projection loss. So what we do over here, we project the estimated and the ground truth key points into 2D space, and then we compare pixel by pixel difference. We have a separation loss that validates that no more than one key point can exist on the same 3D position. And finally, we have a shape loss that forces our network to estimate key points on the surface of the object, not outside, not inside the object. Our approach estimates total n key points. However, all the key points are not valid for any object. For instance, if you talk about a chair, there are different sort of chairs, a simple chair or a complex chair. For a simple chair, we can represent a simple chair using only 12 key points. However, the complex chair cannot be represented properly using 12 key points. We may need more key points for the representation. So that's why our approach estimates confidence score for every key point. So based on this confidence score, we identify out of n estimated key points which are the more useful for us or more valid with respect to the about the structure of a chair. So for that, we have a confidence loss. We have all these losses for training of our network. Here I'd like to discuss how we select the valid key points out of all the predicted key points. For example, here you can see the two tables. One is highlighting on top, like our approach estimates 3D key points as well as the corresponding scores. We select the confidence scores based on the threshold. Like all the confidence scores that are above threshold are considered as valid. Based on this information, we use this information for selecting the valid key points from the all set of estimated key points. And for easy visualization, we highlight them, we show the correct key point, the valid key point on top of the original point cloud. Thanks to the confidence score that allows us to train our model for multiple categories at a time, like for jointly training a model for multiple categories. And secondly, the confidence score allows us to estimate different number of key points with respect to the structure of the object. You can see over here, our approach can estimate different number of key points. For performance comparison, we use the same process, same method as adopted by KPNet. We estimate key points for two views of an object and compute a relative pose between two views. And then we find the angular distance error between the estimated and the ground truth pose. For comparison, the first metric we are using over here is the comparison between the rotational matrix, which is exactly the same as adopted by KPNet, where we are just comparing the estimated and the ground truth relative pose. The second approach is very interesting. Like in this metric, what we are doing, we are representing every point with a vector from an origin, and then we are applying dot product in order to find the distance between two key points in 3D space. We compare our results with KPNet, and we use key point net dataset. Actually, this dataset contains only point cloud and meshes and annotated 3D key points. However, there are no images. So for that, since we are focusing on images, we need images. We render images in 24 different views, and we use them for training of our network. Here's the table illustrating the qualitative results. It can be observed, this table is highlighting the angular distance error between two views of an object. What we do over here, as I highlighted before, we are capturing two images, we are feeding two images one by one to a model, and we are finding the relative pose. So this table is highlighting the relative pose. So it can be observed that the average angular distance error of our approach is approximately 8.01 degrees lower than that of KPNet. Here I'd like to discuss how could we use the estimated key points for pose estimation. Just as an example, I have highlighted two views of an image. We are feeding these two images one by one to the model. And we extract the corresponding key points. We use these key points for finding the pose between them. And then we transform the estimated, sorry. And then we transform the estimated key points of a view A using the estimated rotation matrix and using the ground truth rotation matrix. It can be observed that both the views, both the transformed versions are approximately in the same view. Moreover, it can also be observed that both the version of a view A that are transformed using the estimated and ground truth pose are exactly in the same pose as the pose of view B. We also present the distribution of angular distance error. It can be observed there for most, like around 79.73% of the total test samples, the error remains 0 to 5 degrees. So this experiment highlights that our results, like the key points estimated by our approach, can be used to find the relative pose between 2 point clouds, between 2 complete point clouds. Here we have results for some other categories. I'm not going into the details. As an ablation, we evaluate our approach with and without pixel-wise representation module, like PWR module. Here's the PWR module. The results of the PWR module are highlighted in green, and the results are same as presented in the previous table. We remove this module, and we feed the features directly to multi-layer perceptron after reshape, and we get the results as highlighted here in pink color, like right? So it can be observed that our approach performs well when we integrate the pixel-wise representation module. Here we compare the performance of confidence score. So what we do over here, we use the estimated confidence scores and the ground truth confidence scores for selection of valid key points. And then we repeat the process, we find the relative pose, and we compare. So in first attempt, we are using the estimated confidence score for valid key point selection, and the results, angular distance error is highlighted here in blue. And now we are using the ground truth scores for separating the valid key points, and the results are highlighted in green. We found that either we use the estimated confidence scores or the ground truth confidence score for selection of the estimated valid key points, the results are approximately the same. So this was all from my side. If you have any question, I'd love to answer you guys.
Thank you so much for the nice presentation. Thank you. Any questions?
So, thank you for the nice presentation. My question is about, you have showed the results on rigid objects. So, what do you think about applying your method to articulated objects?
Sorry, I didn't understand your second point.
How can you apply your method to articulated objects? Like humans, robots, or something like that?
All right. Actually, in this research, we are focusing on synthetic data with a fixed set of points. What we do over here, we render images in 24 views. The views are fixed, although we have some errors. But I don't know how could we use them for articulated robot, like a robot, articulated robot, looking at the object in a real environment. So I have not tested that one. Yeah, I have tested on real images. On real images, our approach could not get good results. But yeah, this is the limitation of this approach. We can improve this as well. But this is a nice observation. Thank you.
Okay, second question.
Yes, please.
Thank you. And about You know, you have some pole estimation once you have the key point and make the correspondence. What's happened if the key point detected in different views is not match? How you guarantee that on the key point match? Some kinds of.
Okay, I wanted to go to the slide, but I guess it's not allowing me to move. So actually, what is there?
You can do that.
Okay, sure. We have different losses over here. Let me move a little bit fast. This one, yeah, this one. We have different losses. Like in this loss, can you repeat your question again? Sorry.
My question is about the pose estimation. So you need the matching between the key points in different view, isn't it? Pose estimation.
In pose estimation.
Of your
Okay, well. Actually, we have different losses. Our key points are more accurate for the selected views. For that selected views, we don't have any error between the estimation of the relative pose.
So which means if somehow there are some errors in
Yes,
the matching,
yes, in angular distance error, there are some errors. For example, if we could not estimate the good key points, then for sure there is an error. And this error is actually depend on the iterative closest point, like ISAFE. We use usually ISAFE. Like we have two set of key points, and now we wanted to move one towards second. We need some approach here. So we use the iterative closest point approach for merging the two key points. I don't know if I have answered you in a correct or not.
Yes,
If you have any other, if I could not answer, please we can discuss later as well, in more detail.
Of course, thank you.
So any other questions?
Maybe the one from here.
No. So just a curiosity, you have a number of losses. Did you make some ablation study on the effects of these different losses?
No, actually, in this work, we could not ablation on the losses, different losses, but in the next work, which is the next extension of this work, there we did this thing, and we found that like position loss is more important in our case. Separation loss is not very important after some epochs. In some epochs, in the initial epoch, our key points emerge on the same position. For that, we need separation loss for moving of our key points. But after that, once the key points are spread enough, then we don't need the separation loss. The projection loss, yes, projection loss important. Like we project the 3D key points into 2D space, then we find the distance, pixel-wise distance. So this is important in our case. And the shape loss, yes, this is very, very important. Like in most of the time, since just consider we don't have any 3D information as an input, and we want to estimate 3D key points. This is very, very, very difficult task. So how could we force our network to produce key points on the surface of object, not outside the object, because we have the partial points. Like we don't have any information 3D. So we use this shape loss. Shape loss forces our network to estimate the key points on the surface of the object. So, and what about confidence loss? We discussed confidence loss in details. Like this is very, very important in identifying the valid key points.
Okay, so thank you very much. Thank you. Let's thank the speaker again.
Thank you.
So now we have a remote presentation by Giovanni Pasqualino, and he will give the talk about unsupervised multi-camera domain adaptation for object detection in cultural site. So I'm pleased to have Pasqualino online.
My screen. Okay. Good morning, everyone. Can you see my screen and can you hear me?
Sure, we can.
Okay. Good morning, everyone. I am Giovanni Pasqualino. I am a PhD student and I came from University of Catania. Convolutional neural network work very well to solve classification and regression tasks. However, to achieve good performance, they require many well-labeled images during their training. The labeling process is really expensive in terms of money and time because it must be done by human annotators. A possible solution to reduce this cost is to train these algorithms using synthetic annotated images acquired using an automated annotator tool. However, when we test them on real images, they achieve poor performance because there is a domain difference between synthetic and real images. As we can see in this picture, if we train a state-of-the-art object detector with synthetic images and we test it on the synthetic test set, it achieves a mean average precision of about 92%. But if we use the same model with the real images, it achieves only 12%, even if the two test sets are really similar. Domain adaptation algorithm try to reduce the gap between these two domains. Domain adaptation method work as shown on the left side of the slides. They take as input a pair of synthetic labeled and real unlabeled images, extract the feature and try to align them. In some cases, we can also use some image-to-image translation method, like for example, CycleGAN, to reduce the gap at the pixel level, as shown on the right side of the slides. And of course, we can also combine both methods. However, domain adaptation algorithms take into account only a pair of source and target domains, but in a real scenario, there isn't only one target domain, but many of them that, for example, can be generated from many devices which have different lengths. So this kind of algorithm must generalize across them. Okay. A possible naive solution to adapt state-of-the-art method for multi-target domain adaptation is to merge the target's domain into a single one. To study the problem, we presented a dataset that contains 16 artwork located in Galleria Regionale di Palazzo Bellomo and divided as follows: 75,000 of synthetic images generated from a tool and automatically labeled, 2,000 of real images acquired using HoloLens, and about 2,000 of real images acquired using GoPro. The real images have been labeled by human annotators. We present multi-domain adaptive RetinaNet, which is a generalization of domain adaptive RetinaNet that is able to take as input any number of target domain and try to align them using the gradient reversal layer. In this table, we compare the result of domain adaptive RetinaNet trained using only one target domain at time and testing it on both targets, and the result of domain adaptive RetinaNet trained using GoPro and HoloLens merged. As expected, using both domains during the training, the results are improved on both domains of about 0.6 and 2.5% for HoloLens and GoPro. In this table, we report the result of some state-of-the-art method adapted for multi-camera domain adaptation. As we can see, multi-domain adaptive RetinaNet improved the result of domain adaptive RetinaNet of about 3 and 2% respectively on the HoloLens and GoPro test set. In this table, we report the previous algorithm adding to the pipeline CycleGAN. And as we can see, CycleGAN allows to improve the performance of all methods. In this second case, multi-domain adaptive RetinaNet improved the result of the best state-of-the-art method, domain adaptive RetinaNet, of about 5 and 0.2% respectively on the HoloLens and GoPro domain. We compare qualitatively some detection result obtained by the proposed multi-domain adaptive RetinaNet with respect to the RetinaNet baseline. The ground truth is the blue bounding box, the correct detection is the green box, and a wrong classification or regression is indicated in red. Multi-domain adaptive RetinaNet perfectly recognizes small, large, and partially occluded artworks. RetinaNet is not be able to detect some artworks, detect some false positive, and it usually predicts incorrect bounding box. We extended the multi-domain adaptive RetinaNet algorithm introducing a self-training iterative procedure that at the end of each step produce pseudo-label for the target domain. So in this way, also the higher convolutional layer of the object detector can be trained with the target images. As shown in this table, the self-training procedure improves the performance of multi-domain adaptive RetinaNet of about 20% for the HoloLens test set and about 90% for the GoPro test set. Also, in this case, the results are enhanced if the methods are combined with the cycle gun. The self-training procedure in this case improves the performance of about 8 and 0.8% respectively for the HoloLens and GoPro test set. It is important to notice that this latest method has similar performance to RetinaNet trained with one labeled target domain and tested on the other one. In particular, the results in green are comparable with the result of the proposed method that does not use any manually labeled real images. So, in conclusion, we studied the problem of unsupervised multi-camera domain adaptation. We released a new dataset and we presented neural algorithms. Thanks for your attention.
Giovanni, can you hear me?
Yes, now yes. Probably with the share screen, I'm not be able to hear you.
So
But I can try.
the question is, I
Okay.
read different performance figures when you test on HoloLens and GoPro. So can you explain shortly why this happens?
Just a second. Do you refer about these slides?
Go back to the quantitative measures. Yeah, no, go, yeah, also this is okay. No,
Or maybe this?
So, yeah, 8%, 0.8%.
Okay. Okay. In this table, we report the result of the previous presented method, multi-domain adaptive RetinaNet, and we compare it in introducing the self-training procedure. So the self-training procedure allow to improve the result of 20% and 9% respect to the multi-domain adaptive RetinaNet. The second part of this table report the result of the two previous methods, but including the cycle gun to the pipeline. In this case, the source is translated to the real and then is used as synthetic.
Yeah, but the question was, on the HoloLens, you have an improvement that's very significant.
Yes, probably.
Yeah, on the
Okay,
GoPro,
probably.
it's much less.
Yes, probably on the GoPro, the improvement is less than the HoloLens, because there are some objects in the synthetic source that are not well translated to the real. And I think this is there are some classes that are really hard to detect. So also the translation from synthetic to real is really hard for Cyclegun.
So I understand. Thank you so much. If no other question, we can skip to the next speaker. Thank you so much again. So we have another remote presentation by Mohammad Aris. The talk is Learning Visual Landmarks for Localization with Minimal Supervision. So let's connect Mohammad.
So can you hear me?
Sure.
Yeah, so welcome and hello everyone. So welcome to my talk. My name is Mohammad Haris and I'm a PhD student at Frankfurt University of Applied Sciences. Today I'm going to talk about learning visual landmarks, which is basically an approach to learn new landmarks in a scene with minimal human supervision. So this project is a joint collaboration between Honda Research Institute Europe and Frankfurt University of Applied Sciences.
Mohammad, can you have your presentation in full screen, please?
Yeah, sure. Yeah. So I would like to start by introducing what is visual localization and mapping. So consider we have a robot and it wants to navigate to a goal location. In this case, a charging station. So there are two fundamental prerequisites to achieve this task, namely localization and mapping. Localization determines the current pose of a robot in an environment, while mapping creates its consistent model of its surrounding. And the term visual refers to the use of cameras to solving this task. So this localization and mapping are basically two fundamental prerequisites for intelligent behavior. So this visual localization and mapping area is a well-researched area, and there exist a lot of methods in this domain. So I would like to highlight a few approaches in this domain. So most precise among them are structure-based methods that basically localize a Curie image relative to a 3D point cloud reconstruction. In contrast to using a 3D point cloud, image retrieval approaches basically match 2D features of a Curie image to the 2D features from an image database and estimate the Curie by the most similar database image. The recent development is that we have now absolute pose regression techniques that learn to regress a pose from an image directly. So they train a neural network in an end-to-end way, so where the network outputs the pose of the image. On the other hand, we have bio-inspired approaches that basically train a hierarchical model and reproduce the firing characteristics of planes and the head direction cells found in rodents. So all these approaches basically are sufficient to estimate camera position and building effective maps, but they lack semantic information. So why do we need it? So basically this information can help a robot to basically perform other high-level tasks besides just mere localization. So this can enable other tasks like human-robot interaction and other task-driven navigation. So our recent basically project in this direction uses unique regions as shown in the figure, and basically learns to localize from these unique regions instead of using the complete image. And here each unique region basically gives an independent estimate of the robot position. And later we combine these estimates to give a global position estimate of a robot. So this approach basically scales very well to a large scale environment, but it requires cumbersome hand labeling, because if you move to a scene and you don't have pre-learned unique regions, then you need to train those first before using them. So the conventional way is that you train a neural network to recognize them, but for that you need a lot of labeled training data, which is very hard to generate. So in this work, our goal was to basically minimize this task, or to have a minimal or ideally no supervision for learning new landmarks in a scene. So what we do here is basically consider we want to learn this painting on this wall as a new landmark. So as I said, the conventional way is to use hand annotation and basically label lots of images and then train a neural network to detect this. What we do differently here is that we use the standard detector or the objects that have pre-trained detectors. For example, in this case, this bicycle. So you can easily find a bicycle detector now these days, for example, from YOLO. So what we do is that we use these objects as anchor to generate the label training data for new basically categories. So a comment on these objects, because these objects are typically mobile, so they are not suitable for providing long-term localization, but they are very much suitable as mobile teaching anchors. So what we do is, the idea is to place such an object in a spatial relationship to a new landmark and generate label training data. So these are the steps. So what we do is that obviously we need to first place this, or basically the object with the pre-trained detector in a scene, and then we record a video with the mobile robot. Afterwards, we use a pre-existing object detector and apply it on the images to detect its instance in the screen. And at this point in our basically approach, we need a human supervision because the human needs to specify the spatial relationship between the anchor and the landmark, which in this case is the top area of the bicycle. But we need to do it only once for a single image, and based on this specification, we can generate the labeled training data for all available training images. So what we do now next is that we train a new detector that learns to detect this new landmark. And once the training is done, we can optionally remove this anchor because we no longer need it in the localization and mapping phase. Before going into the localization pipeline, I want to introduce a short or give a short overview of slow feature analysis, because this is the core algorithm we use to learn spatial representation of an environment. Basically, it is an unsupervised learning algorithm that extracts slowly varying features from a quickly varying input signal. And it can be used for a lot of different tasks, such as classification, dimensionality reduction. But here we use it to basically encode spatial representation. So how do we basically use it? So the basic idea is that the primary sensory signal typically vary on a faster time scale compared to the significant information, in this case the robot position. So consider if we track a value of a single pixel over the complete image sequence and plot it as shown on the right, you can see that this value varies much faster than the actual robot position in X and Y. So this is the main thing we do, is that we on the input we have such fast varying signals, but then we apply slow feature analysis to it and extract the latent representation, which in this case should ideally encode the position of the robot in space. So mathematically, it is defined as an optimization problem in which the objective function is to find instantaneous input-output functions that minimize this delta value. It measures the temporal slowness, basically, and it is performed under three main constraints: that the output signals have zero mean, unit variance, and they are decorrelated, which means that each output signal should code for a different aspect of the input. So this slide shows the mapping pipeline. At the input, we have obviously an input video for the mapping and localization phases. Now what we do is that we apply the learned trained detector from the previous phase and basically detect the new landmark in the scene. Afterwards, we extract this new landmark from the scene and resize it to a fixed size. And then we use basically this image stream to train a SFA network, which then learns to regress the camera position relative to this landmark. And in the end, obviously, we have learned representation relative to this landmark. And the procedure basically is the same for all the landmarks in a scene. And then basically, yeah, so this is an implicit representation in slow feature domain. So to basically have basically the performance evaluation in the metric space, we basically learn a simple linear regression where we map this SFA representation to basically a metric space representation. And then we basically, as I said earlier also, that we combine these individual estimates using weighted average to have a final robot position relative to each landmark. So this slide shows the experimental setup. We basically tested in 2 different outdoor environments that are basically unstructured garden-like environments that basically differ with respect to their size and complexity. So for data collection, what we did is basically we recorded 3 different recordings from each of the environment, and these environments basically differ with this. These recordings basically differ with respect to dynamic scene variation and lighting conditions. And we have basically 3 different recordings from each area. And what we do for testing and evaluation is that we use one of the recording to train the network and the other 2 independent recordings to test the method. And to compare it with other approaches, we use also Fourier SFA, which is basically what we do is that we extract Fourier features from the images, and then we learn SFA representation using these Fourier features. And the POSNet is basically end-to-end learning based method, which basically regress the pose from the image directly. So these are the experimental results. So the first scenario is temporal generalization, in which the train and test data comes from the same position or the same trajectory of the robot, but in over different time intervals. We conducted this experiment in both environments. So as this table basically shows you the median localization performance for the landmark based localization and the 2 compared methods. So each ID basically shows the localization accuracy relative to a single landmark, and then this combined column shows the achieved performance using the combination of all of the landmarks. So as you can now see that the landmark-based approach performs on the same level most of the time, but extremely better in a large-scale environment, which is very complex, and it basically produce better results than the other methods. So the effect of this is that we can using this approach, we can basically scale the localization to large scale environments as well. The second test scenario is spatial generalization, in which the environment is almost similar, but the test and train trajectories come from different robot positions. So what I mean by that is that we record the robot position on this red line as shown in the figure, but for the test cases, we took all the images from the in-field conditions, so the in-field area. So again, the table shows you the same information. In this case, where the approach achieves similar performance to the baseline methods. However, it degrades in this scenario, but we can basically further improve it using sparse images from the infield as well. Yeah. And then this last experiment basically shows that how our approach scales with the number of landmarks. Also, basically, this is the plot shown when you basically, we have used simulated data versus real world data, and in both plots basically show the similar characteristics. So initially, by adding more landmarks, the performance improves significantly, but over longer time, or so adding more and more landmarks, the performance saturates as expected. Yeah. So to conclude, in this approach, we basically we introduce a new approach that basically speed up the label generation process for learning new landmarks for visual localization. And this technique uses the readily available CNN objects as anchors to generate label data for the unseen imagery. And then later we use these landmarks to basically perform basically localization relative to these, and these basically show very good performance, especially in a challenging large scale outdoor environment. And this performance can be significantly improved further by integrating more landmarks. So from the application perspective, our system is basically suitable for robots like lawn mowers or vacuum cleaners, that basically comes with a pre-existing visual detector to learn new landmarks in a scene. Thus, our approach enables reliable localization in the long term, even if the anchor objects are basically no longer present in the scene. So I thank you for your attention, and happy to answer your questions. Thank you. So I cannot listen you.
Hear me?
Yeah, yes.
So you talk about using anchors to learn new landmarks. So
Yes.
the question is, do having more anchors help eventually?
Yeah, so basically in our approach, you need one landmark per, so one anchor per landmark. You want to learn if you want to basically have a single recording and which you can later use. So ideally at the at the very first step, you want to have a single basically anchor per landmark.
And the location of the anchor does have influence on the detection, the learning of the new landmarks?
So yeah, so basically this is where the human input comes in our learning paradigm. So basically the human would ideally place those anchors at those locations where basically there are unique regions basically, and to basically facilitate this label generation phase for the robot.
Okay, thank you so much.
Well,
If no other questions, let's thank the speaker again.
thank you.
Now we have the sixth presentation by Jiri Mampa, and the talk is leveraging road area semantic segmentation with the auxiliary steering task.
Yeah, so hi, my name is Jiri Maanpää. I'm from the Finnish Geospatial Research Institute, FGI, and I'm here to tell you about our work on leveraging road area semantic segmentation with auxiliary steering task. I'm also a doctoral student at Aalto University. So the main motivation in our research is that there's a lot of challenging driving conditions in Nordic countries. We have a regular winter time, so the road might be fully covered in snow, and then we have a lot of gravel roads, and there are many places that you can't reach without driving on a gravel road. And these might be difficult scenarios for autonomous cars, as they quite often rely on having lane lines and that kind of stuff. So we need to somehow train those convolutional neural networks which do the pattern recognition. We need to train those with these kind of data sets. But you can think that you have to have quite a lot of data because there's a lot of different weather types and a lot of different road conditions, and if you combine all of them, there's just too much of data. And of course, you could try to annotate it, but it will be quite tedious, so you need to do something else. As we have seen in many presentations, many people try to avoid this annotation. And of course, you can use domain adaptation and transfer learning as one solution. But of course, so that's one approach, that you can somehow adapt to new datasets even though you don't have the ground truth. But in this work, our viewpoint is that autonomous cars, they already kind of like produce a lot of different sensor data. So you can record steering wheel angle and speed, and you can have different camera and LiDAR modalities or sensor modalities that you can. So if you can, for example, predict those from camera image as an auxiliary task, you can support the pattern recognition tasks to improve the performance. So this is one example of the idea. So we are trying to improve road area segmentation with auxiliary steering task. So we are training a multitask learning model, which in one dataset does road area segmentation, and in another dataset it does steering wheel angle prediction. And this another dataset, it has a lot of challenging driving conditions like snowy road and gravel roads and that kind of things. And our goal is that in the end, the model will do also good road area segmentation on a target dataset. So even though it hasn't seen snowy conditions that much, it could still detect the road via this kind of training. And we assume that this should work because steering the car and seeing where the road is are quite similar things, so this should work. And also we chose this road area segmentation because it's quite important if you want to stay on the road in these conditions. And now I tell you briefly about the methods that we have used. As a source dataset, we had mapillary vistas. So it has a lot of segmentation classes, and we combined those to one road area segmentation class. And then we have target dataset, which is FGI autonomous steering dataset. It's a dataset that we have collected on our own, and it has steering wheel angles corresponding to RGB images, and we have quite a lot of samples. And then we also annotated 100 samples for validation and 100 samples for test set. We annotated them by hand so that we can measure the performance afterwards. How well does the model adapt to this target dataset? And this is the model that we used. It's from the work of Van Hende et al. They have this good work with MTINet, multi-scale task interaction network. And it's a good way if you have image spatial like tasks like depth prediction and segmentation. You can combine those kind of that kind of like tasks easily together with this kind of network. So you have features in 4 different scales from the backbone, and within each of these scales of features, you do initial task predictions. So you're actually trying to predict the road area and the steering wheel angle in each of these yellow or orange modules here. Then those predictions propagate to the higher scale, of course, with these feature propagation modules. And as you have all initial task predictions, you fuse the tasks together with these multimodal distillation modules. And then you fuse all the resolutions together with these feature aggregation modules. And in the end, you will have a road area segmentation mask, and then you have a steering wheel angle prediction. But you can see that the steering wheel angle is a number, so you can't just fuse it with an image easily. So this is the way that we found which works. So we have a steering feature which has 4 channels, and it's an image. And we actually do both a road area segmentation and steering wheel angle prediction based on that feature. And this might sound quite special, but as we train or have this road area segmentation loss also applied on the steering feature, it will look more like of a road. Otherwise, it will be something generic, and the data and then the steering will not be fused with the road area segmentation. So, as we have both this road area segmentation loss and steering loss applied, or predicted from the steering filter, it's a way in which we can easily fuse the steering information with this road area segmentation mask that goes through the model. And of course, we need a transfer laning baseline so that we can compare that, okay, if we have just transfer laning and if we have steering, then how much benefit we get from the steering. So this is one standard thing that we used here. We borrowed it from the work of Cheng et al. With this unsupervised scene adaptation, and we didn't implement everything there, but one of the, like the first stage from there. So if you have a sample from a source dataset and you have the road area segmentation mask, then you of course evaluate all the segmentation errors, also from the initial task predictions for training purposes. So, and then if you have a sample from a target dataset, you have the steering wheel angle, so you evaluate the steering wheel square error and loss for that. And then you have also two discriminators, one acting on the primary segmentation mask and one for auxiliary segmentation. So those discriminators try to predict if the sample is from the source or from the target dataset, and therefore we can decrease the domain gap. And this is something quite simple that we have as a baseline here. And then I'll discuss our experiments and results. So kind of like we have three models. We have single task model, which is trained only with this mapillary dataset, and it does only segmentation. And it doesn't know anything about this FGI dataset, so it doesn't know, it hasn't seen those adverse conditions. So you can assume that it's not that good, but it's a baseline anyways. Then we have this transfer learning model, which is kind of like the model that you have seen before, and it has seen the new dataset, but it doesn't know anything about steering, so it's not trained to do the steering on the dataset. And then we have our multitask model, which does both road area segmentation and steering prediction. That is the full model that you have seen on the previous slides. And so we can compare the performance between this multitask model to this transfer learning model, and then we can see how much performance we get if you use steering in this training. And we repeat these experiments with HRNet and FPN ResNet backbones, so we can confirm or have more validation on the results. And here are the results that we got. So we had 100 samples in validation set and 100 samples in test set, and these are the road area mean intersection over union values. And of course, you can see that with a single task model, you don't have that much performance, and as you apply transfer learning, you get even more performance. And in validation set, we see quite solid increase in accuracy, that we get 1.4% increase with HRNet backbone as we apply this steering training. And with the FPN ResNet backbone, we get something like 1.8% increase in this mean intersection over a union. And then we were happy with the results and decided to evaluate the test set results. And it was a bit surprising that with the HRNet backbone, the increase was just below 0.1%, which can be just pure luck or kind of like random noise. It's kind of like not so good. But then with the FPN ResNet backbone, we found out something like almost 3% increase, which is kind of huge compared to the other accuracies. And it's even better than the HRNet backbone, which is usually better. So there is some uncertainty here. We assume that it's mostly because we have just 100 samples in the annotated or in the test set. So failing in one sample kind of like can mess the results. And of course, as you do machine learning, you have this validation set and optimize the model performance in validation set, so that it's quite unavoidable that you have this bias. And also, these are quite high mean intersection over union values. So if you want to, so even humans might have different opinions, kind of like what should be classified as road and what not in some accuracies, and we are quite close, somehow close to those. So it might be difficult to measure performance differences. And here are some examples of the FPN ResNet models in which we had this 3% difference in accuracy. You can see that the single task model isn't that good, and if you use transfer learning, it's much better, but you have still some holes in the segmentation mask and also some stuff outside the road, which is kind of like not classified correctly. But in a proposed approach, the road edges are a bit more clear, and you can see the road further away, but still there might be some errors, of course. And therefore, as a conclusion, we have implemented the multitask convolutional network with auxiliary steering tasks to improve road area segmentation performance. And we observed that 0.1 to 2.9% increase in road area mean intersection over union with our model. And therefore, we would say that finding auxiliary tasks to support other pattern recognition tasks is a promising future research direction in autonomous driving. Okay, so thanks for your attention, and I'm happy to answer your questions.
So we have one question there.
Thank you for your talk. It was a very nice talk. I imagine that the driving steering wheel is very useful information if you have a single lane, a single car driving. What happens if you have intersections or multiple lanes to detect? How does it deal with this?
Can you get your microphone nearest to the mouth, please? To the question.
Yeah, I understood the question. Kind of like, I would say that it depends. Kind of like, if you go usually in the intersections, you go straight. So, kind of like, we didn't kind of like focus that much in this kind of like scenario because our data set is more like driving sequences, and we drew a lot of curvy roads in kind of like the rural landscape in Finland. So kind of like there were very that much intersections. Usually in the intersections also you usually go straight. And actually if you turn in intersections, we actually excluded those from the dataset because if you want to predict steering and you are doing a turn in intersection, you just can't predict it. So they were excluded in the dataset.
Okay, thank you.
Any other question? Yeah.
Thank you for the talk. It's very interesting. I wonder what if the weather is bad, like rainy or something. Do you consider this condition?
I'm sorry.
Like when you have rain on the camera or something.
Yeah, kind of like we have less rainy conditions in this data set. We have some, but I don't know. It's kind of like a small fraction in the data. And the camera was inside the car, and we had car wipers kind of like used. So I would say that for example, the drops on the glass wouldn't matter that much. So most of the kind of like challenging conditions are that there's no snowfall, but the road is kind of like covered, or road is unusual.
Thank you.
So thank you for the clarifications. Any other questions from the audience? No, if not, let's thank again the speaker. So now we have the very last presentation of the session, which is a remote presentation by Dario Fontanel. And the talk will be relaxing the forget constraints in open world of recognition. So let's connect the speaker, please.
Hi, good morning, everyone. I hope you can see my screen and
Yes,
hear
we can.
me.
We can.
Okay,
Yeah.
perfect. So again, hi everyone. This presentation is titled "Relaxing the Forget Constraints in Open World Recognition," and it is a dark work done together with my colleague Fabio Cermelli, Antonino Geraci, Mauro Musara, Matteo Tarantino, and Barbara Caputo. So the context of this work is the image classification. So we are here interested in assigning a single class label to an entire image. So we are not interested in defining multiple objects inside a single image. And I'd like to start from the preliminaries of the work. So most of the common machine or deep learning approaches are trained under the closed world assumptions, which means that a model is supposed to recognize at this time the same exact categories on which it has been trained on. As you can see in this case from the picture, at the training phase, the model is able to learn what is a car, a bicycle, a motorbike, and when it is deployed, of course, it should be able to recognize all of these categories. But actually, it is not like the general scenarios, because it could happen, and of course, when the model is deployed to the real world, it is likely to happen that it will encounter also categories that it has not already seen, as in this case, the airplanes. So a model that has been trained under this assumption, of course, is not able to proactively react to this situation, and the open world recognition, that is the task that I'm addressing it in this scenario, aims to solve. So to have our view of how the open world recognition scenario works, let's again see at the pictures. So let's suppose that at a certain time in a certain point in time t, a model has been trained on bicycles and cars categories, and of course it has been able to recognize them. Then when the model is tested, it's likely that it will be tested on both known and unknown categories, as you can see here, on both cars and airplanes. And the model in open recognition task needs to perform two main actions. The first one is to actually detect that there is something that he has not already seen. So there is something that in this case is called an unknown category that does not belong to the knowledge that the model has acquired during training phase. And the second action that it has to perform is that once a new data set of the novel category has been collected, it has to incrementally extend its internal knowledge to be able to, at the end, finally recognize both all the previous categories and the new ones based on the novel added training data sets. So this is the general scenarios. Of course, in this scenario, we have many challenges. We will focus on mainly on two of them. So the first one is the detection of the unknown, so the capability of recognizing an image as something that does not belong to the previous knowledge of the model, and of course the incremental learning phase, in which the model has to extend its knowledge to be able to recognize from now on the new category. So let's focus on the second one that will allows us to understand better our contribution also in the first one. And so just to have a brief preliminaries on what is incremental learning. Of course, when we are trying to learn new classes, the model needs to change basically its internal weights, its internal parameters to be able to recognize them. This change may change the weights from the ideal situation in which they were before to recognize the previous classes. So this is the phenomenon called catastrophic forgetting, in which, again, basically, once the model is asked to learn novel and novel categories, more and more of this kind of categories, it gradually forget the previous ones because the weights needs to change to actually be able to recognize the novel ones. So this is a general, a common known phenomenon in incremental learning. And what we have as a partial solution, I would say, is the knowledge distillation paradigm, in which we are in the different training steps, we are forcing the model of the current step to emulate the behavior of the previous model on the previous step, because the previous model is supposed to be the best model that can recognize the classes until its own step in time. So this is the general paradigm, but our intuition starts from that, start from this, and it says that in some situation we could at least avoid the emulation of the previous models when the previous model is uncertain, because of course emulating the previous model when it is not sure about which is the right classes to predict may lead the current model to actually learn wrong representation for the categories that you are thinking of. So this is our intuition, and we started to develop basically two main contributions, two main losses that we'll see in a minute towards this objective. So the first one is called polyloss, which is a different ways of encoding the knowledge distillation paradigm, in which we basically have tried to relax this kind of binding that there was in the network, and in this case we are able to avoid the situation in which avoid the emulation of the previous model when it is not sure about the prediction. And as you can see here, this phi of the phi indicates the outputs of the models, and the t, of course, indicates the current time. So t-1 indicates the model at the step directly before. This loss again leads us to fine results that we will see in a minute. But in certain situations, we realized that this loss can be still too binding. So we decided to actually release again, do a step further towards this degrees of freedom of the model, introducing an additional loss, which is called the forget constraint relaxation, in which basically we actually, sorry, it's not a direct loss, it's a strategy to weight the loss that we have talked before. In which basically we, in this strategy, we randomly removes some of the loss contribution. As you can see here, the weights of the loss is depends on a probability, and when the probability is 0, the weight of the loss is 0, and so the contribution of the loss is 0. And in this case, we are avoiding certain situation in which again the model could benefit from not being forced to emulate the previous model when it is not sure about the prediction. And so this has been the two contribution that we have made towards the incremental learning phase. And yeah, in a minute we will see the final results. But let's speak a little about the detection of the known, which is the second challenge. So in this case, we want to learn a rejection threshold for which lower probability values are considered uncertain. And in this case, in that case, the sample is considered as belonging to an unknown category. So previous models, previous state-of-the-arts, as you can see from the picture, were used to represent the feature space as the left picture, in which they were used to consider the feature space as made of circular clusters. We have evaluated that maybe this is not the ideal scenario, this is not the ideal case, because as you can see from the picture of the right, which is the feature space that has been modeled by us, it allows to avoid the misclassification on some of the the black dot that in the previous model were classified still as belonging to some of the categories. They, of course, seemed as outliers, but they were still classified as being some part of the known categories. In this case, with the new loss that we provide, we have been able to shape in a better way the features boundaries, and in this case, we are able to classify the unknown samples as correctly as unknown samples. So again, this has been the loss that we used to learn the detection, which is this term over here. And moving on to the results. we have benchmarked our contribution in 3 main datasets: Core 50, RGB object dataset, and Cypher 100. They are mostly most of the datasets are about everyday objects, everyday life objects, while Cypher 100 is more similar to general objects that we can see, for example, in this case, airplanes, cars, and and other vehicles. As you can see from the plots, our method is able to achieve the state of the art in each of the benchmark we used, and in this case we are evaluating it under the standard open world recognition harmonic mean, which is the standard metric that is used in this scenario to evaluate the models. So this was the presentation. Thank you again for your attention. And of course, if you have any question, please feel free to ask me. Thank you.
Thank you for the presentation. Questions from the audience? One question there.
Hi, thanks for your presentation. I'm wondering why the polyloss is a generalization of the knowledge distillation. You said that, but I miss the why.
Yeah, actually, it's not a generalization. Is still a distillation loss because we are still using the prediction of the previous model, but we have encoded it, as we can have seen from the formula, as a polynomial function that allows us to approximate it a certain degree. That in the case that we have used was on 3 degrees. And in this case, in some situation, this loss have avoided the general, I would say, banding that the standard BC is, but the binary cross entropy has, because in this scenario we are kind of reducing basically the entire entire binding that the binary cross entropy has, because we are not modeling the entire prediction, but in this case we are only focusing on some certain of them, thanks to the degree that we can choose from the polynomial version of a loss, because of course modeling a function with a polynomial function allows us to choose basically which degrees of freedom we want to have. In this case, having a 3 degree allows us to avoid some contribution that could damage the final prediction. Instead, with the standard binary cross entropy, you can choose basically the contribution. You have to weight all of them. In this case, we are not able to remove some of the contribution that are again that damage the model because they are made for wrong, basically, samples.
Okay.
Yeah,
Thanks.
I don't know if I have answered your question. Yeah, thank you.
Yeah. Thanks, perfect.
Cool, thanks.
Thank you. It was a long explanation, so we thank you for that. So, other questions? Yeah.
Hello, thank you for the presentation. Just a question. Do you plan to compare the proposed rejection metrics with some state-of-the-art methods for quantifying uncertainty, such as maybe Monte Carlo dropout or other technique for estimating epistemic uncertainty?
Yeah, thanks. This is a great point. Yeah, we are like we didn't have choose the further direction yet, but of course this is something that we are really looking into it, because also the previous state of the art in this scenario haven't been compared to as you mentioned, Monte Carlo dropout and other also, I would say, out of distribution, plain out of distribution detection method. So we definitely are looking forward to it in our further research. Yeah.
Hi. I'm just curious about the incremental learning pipeline. I mean, when you detect an unknown class, then I imagine you request some labeled data for the new class. And when you do the incremental learning part, are you using only data from that class, the new class, or you're using a mixture of the also the previously seen classes?
Thanks again. This is another great question. In this scenario, so let me just take a step back. In incremental learning, there are different ways to incrementally extend the knowledge. There are some models that exploit previous samples in order to like partially avoid the forgetting. Others they don't. In this case, we are focusing on the first one, which is usually called a rehearsal paradigm. And in this particular case, we are using the entire dataset of the new class, plus the addition of some selected sample of previous classes that are stored in a memory. And of course, since this memory needs to be like a fixed budget, because in real scenarios we cannot have infinite memory, while the new classes are being added. So whenever the number of the new classes grows, we reduce the amount of data that we can store per each single class. But yeah, to just give a brief answer, we are using the entire new dataset and a small selected sample of the previous classes that should be the most representative ones of the previous classes. Yeah.
So about that, do you have any special policy to exclude the classes from the memory?
Yeah, like general, one good rule of thumb is to keep only the samples that are similar to like I would say an ideal representation of the class. So in practice, usually having all the samples of a single class, we compute the features, we compute the average of them, and then we take only the sample that are whose features are most similar to the average that we computed before. In this case, we are able to keep only the most representative samples that should be the most similar one to the average of them. And yeah, and of course, we set it a constraint that was 2,000 samples globally, but this depends on the development, I would say, environment in which we are planning to use this kind of algorithm.
Okay, thank you so much.
Thank you.
If there are no other questions, we thank the speaker again.
Thanks. Bye.
And close the session. Thank you for the attendees. Thank you.